Good morning, everybody. So today let's study sampling and maybe a little bit modulation using continuous time Fourier transform. Then we will study in the second half of the lecture discrete time Fourier transform. And next week we finish with again discrete time Fourier transform and DFT, discrete Fourier transform. So it's like today we discretize the time and next time we also discretize the frequency for numerical implementation, right? You are using FFT, that's DFT, which is implemented in a very efficient way. Discrete Fourier transform where both frequency and time variables are discrete. So they are numerically implementable, right? So I think I can go to, I thought for sampling the slides are really nice, the slides of the textbook. So last time maybe we started with this a little bit, I guess. Let's see. So let's continue. Okay, so we will study sampling in the frequency domain, okay? So then see the effect of sampling on the Fourier transform of the sample signal and reconstruct the signal from samples. So actually what we're studying when we talk about sampling is a continuous time signal, right, goes in. Maybe for this problem, guys, always remember the most easiest example is the recording of some audio or music signal, right? Because that's a continuous waveform. For instance, my voice is reaching you at this moment when you guys speak to your friends, right? And when you record this currently with the microphone, or me actually, when I record this with the microphone of my device, that's doing this. This is the idealized version, but it's actually implementing this continuous to discrete converter, right? Because at the end, you see continuous time signal goes in, and look at this, a discrete time signal. So a sample signal. This is a sample signal, right? A sample signal goes out. So this is the system you see in the box. So we study an ideal continuous to discrete converter. Last time we said actually we can do this mathematically with an ideal model through actually a function called an impulse train. So we multiply the signal, multiply the continuous time signal. You see here it's a multiplication with a impulse train signal, this guy. Remember, this is here, what is the important parameter? Which parameter we should be really setting here? Guys, you see it, I think, in the slide also. What is the parameter, important parameter we have to define in order to carry out this sampling? How frequently we sample, I think TS, right? The sampling period or sampling frequency. Yes, thanks, Evren. Exactly, TS. Here it is, right? This guy. This should be specified, of course. Should be specified. It's a parameter. TS parameter to be specified, okay? So then actually once we obtain this sample signal, this is a notation difference between the two. Actually convert to sequence. Let's see if there is any, guys, okay, this was equal. I hope the mathematics are fine here in the slides, but okay, so actually remember xs of t, when we sample it every ts seconds, right, and is an integer here, actually that gives us our sampled sequence. So remember, it's really like this. I have a continuous time signal. I take samples like this, right, from this signal, And actually these sample values are brought to, I see here, sorry, here, to a sequence. That's it actually. Now that's it. Now this was T, this is N, right? I think it must be hopefully clear for you now by now. I mean, this is X of N, this is X of T, and actually X sub S of T if I'm talking about the sampled one, right? Yeah. So this is impulse train sampling. We had a problem last time with the, okay, I remember we had to show it from the desktop. Okay, so let me show the pictures and we can go to the desktop for viewing the slides with mathematics. This was the idea actually. So you see at n equals 0, n equals 1, x of ts, x of 2ts, x of 3ts. You see, currently we are showing this sample signal, which is x sub st by weighted impulse functions, right? So mathematically, ideally, we can still represent them in continuous time, but then we go to actually the sequence here, discrete time sequence. So what we are doing now, guys, is studying this in actually Fourier domain. So, okay, we should go to the, all right, so let's see. Let me, interesting, it doesn't show at all. All right, so now I recalled this was a problem from last time, which is fine. We can just go to the, I think from the desktop we were fine. So this is, which one is sampling? Here is sampling. Just let's start. Okay, so I won't be able to write on it, but it's fine. Okay, so, okay, yeah, for what is the Fourier transform of this sample signal? So this is really, you see, multiply x by impulse train, and we know impulse train actually samples, right? Samples meaning just takes a sample from this x of t at the argument value where t equals nts actually, where this delta of t is non-zero. So that's why this equation at the bottom of this page is valid, right? So I hope everybody is clear from, like by looking at this block diagram or diagram of the system at this point, do this multiplication or product of two signals, and x sub st is actually the sampled continuous time signal. We just convert it to seconds, right? And you see we really take every ts samples. It's in the equation too. And we've seen this. This is also illustration through some sample signal, okay? And this was, now, what is our goal? Guys, just remember, if you are lost, or even if you are lost, we are back now. We will now take these guys to the Fourier domain. This was time domain mathematics, right? Now, we studied sampling in frequency domain, okay? So to do that, first we have to convert impulse train to its Fourier domain representation. Remember, we derived this, I think, either last time or previous week. It's another impulse train, right? And remember the duality between Fourier transform, time domain and frequency domain. When a signal is, for instance, this or periodic impulse train, let's say, is TS sampled, its Fourier transform is, its intervals are 1 over TS. I mean, so that's what I try to say. This was, let's say, the periodic impulse train. You see, it's a sampling signal, right? It's very obvious. It's separated by TS samples. Okay, now because it's a periodic signal, I can find its Fourier series representation. We did this from the Fourier series analysis definition, and we found it to be 1 over TS. Now, remember, this is the Fourier series representation of the periodic signal. And we have here, important thing is the sampling frequency, right? When you look at such a periodic signal, what is the frequency? You find its period, which is TS, then this radian frequency is 2 pi over Ts. And from what we've derived before for a periodic signal, the Fourier transform is shifted impulses, right? And it's actually shifted to multiples of the harmonic frequency. Here it's the sampling equivalent to sampling frequency and times AK. Remember, it was 2 pi times AK. That's why we have 2 pi over Ts. So guys, I hope it's clear. This black graph here is the signal in black is the time domain, periodic impulse train. The signal shown in red is the Fourier domain, or it's the spectrum of this impulse train, okay? Are we clear until here? This was from before actually, so. Okay. Okay, this is trying to say also, because this was a periodic signal, and this assumes that we remember the properties of Fourier transform. Remember, when we multiply the time domain signal by a complex exponential, we have frequency shift by this Ws amount in this case in the frequency domain. That's why it's trying to say actually we can do this derivation, but I think we must have done it at some point. I think we uploaded these slides, so I hope you guys took a look. Here, the shifted impulse you see is in the frequency domain. I mean, Fourier transform shows the frequency, expected frequency shift. Okay? All right. All right. Okay. So, I mean, for you, even if you are maybe lost at this point, don't get lost. Just catch up here at this point. This is the actually Fourier transform of this periodic impulse train. Actually, this is a little bit more general. You can see that this is for a periodic signal whose AK or Fourier series are 1 over Ts, but which is of course periodic impulse train. I see that the frequency response, right? Let me see. No, we are actually at the excessive T. Sorry, currently we are at looking at the sample signal. Of course. Guys, now we are deriving the Fourier transform of the sample signal, okay? I was talking about this delta, this part only, but now I see we talk about convolution with the signal itself. Okay, I didn't see this x of j omega. I was just looking at this part. And now it should be fine. We try to find the Fourier representation of x sub st. It's a product of x of t and the periodic impulse range. So product, remember, or multiplication in time domain is convolution in frequency domain. Now it's actually take any signal to be sampled, x of t, its Fourier transform will be shifted by these impulses because it's a convolution. Okay? That's why now actually the sampled signal is, this is very important, has a frequency spectrum which has the original Fourier spectrum X and its shifted replica. That's the main actually point of these slides. Is this clear? This is very important. Maybe you can just neglect the derivation. This is actually just result of this bottom line here. Any signal X in time domain, take its Fourier domain representation, Fourier transform, x of j omega. When we multiply that signal in time domain by a periodic impulse train, we convolve this signal spectrum by another impulse train, right? That's why x of j omega convolution by shifted impulses is itself shifted. Okay. This is it actually. This is the derivation. I hope this is clear. Now we look at this on a picture. I think it will become clearer. Just remember this. Infinitely many replicas of the same spectrum shifted to multiples k, right? The multiples of the sampling frequency. This is important. That's why we have to pick the sampling frequency carefully. That's the idea. So here, for instance, this is just an illustration of a typical band limited signal, okay? Band limited because you see outside WB minus WB, the signal spectrum is 0. So it's really typically like you see, I mean, we show it like a low pass signal, but it can be otherwise, of course. Now we try to plot what this equation tells us. Take x, for instance, for k equals 0, it's the centerpiece itself, right? It's x of j omega itself. K equals 1. Shift this spectrum to omega s, right? K equals 2. Shift this spectrum to 2 omega s. This goes on forever. Now k equals minus 1. Take this spectrum, shift it to minus omega s, you see. K equals minus 2 shifted to minus 2 omega s. And again, you see we have infinitely many replicas in both sides, and magnitude of the spectrum is multiplied by 1 over Ts. Guys, do you see a constraint here? Do you see the constraint on, or the relation between the bandwidth or the maximum frequency in the signal, omega b, and the sampling frequency, in order to avoid overlap between these replicas, right? Because if I have overlaps in the spectrum, my signal will be distorted, right? When they are nicely separated, as here, the signal can be actually later reconstructed from its discrete samples, the continuous time. So think of this as, again, this our classical example. We digitized our song, for instance. You are in a concert, you have a microphone, you digitize that song, stored it, you can do some manipulation, but now you want to play it again, right? Now it's discrete to continuous converter through a speaker. If you have overlapping replicas in your sampling, if you don't do your sampling correctly, you can't really replay the original sound, right? Or song. I hope that's clear what I'm trying to say. Is that clear somehow? Yeah. Özgür, I'm seeing you, so do you guys see the problem when these replicas would overlap? I mean, it becomes another signal, right? I mean, it would distort, because you see in that case, look at this original image, the spectrum. The negative frequencies are, let's say, these yellow bands, positive frequencies are this white band, right? In the sampled spectrum, if there is a problem here in our sampling signal, these frequency, I mean, this yellow negative frequencies are mixed with white positive frequencies. That's the problem. So our constraint should be, guys, look at this end of the first trailing or first replica. WS minus WB should be larger than WB, right? Not to have a overlap. Does everybody see this, guys? Look at this end, the negative end and the positive end here. WS minus WB should be greater than WB. That's equal to WS greater than 2WB. Okay? This is the other case, what I was talking about. If we don't pick, you see WS less than 2WB, meaning the sampling frequency, if it's not picked twice, at least twice the maximum frequency in the signal or bandwidth of the signal, then the copies of x of j omega overlap and we have aliasing distortion. This is called aliasing distortion. This is where, like I said, this negative frequencies in the signal in the signal spectrum, you see overlap with positive frequencies. And now in the end, these overlap and we have a completely different spectrum, right? So when we reconstruct the signal from this spectrum or this spectrum, from here, for instance, I can ask you, now I want to go back to the continuous time spectrum, the original spectrum. How can I do it? How can you design a reconstruction system? Just look at the spectrum. Remember your Fourier transform filtering knowledge. We want to pick only this spectrum, right? We would need, yes, exactly, thanks everyone. We would need to do a low pass filtering. That's a reconstruction system actually from sampling. So that's a ideal discrete to continuous converter, you see. But now imagine that that low pass filter on top of here, it's getting a scrambled signal. That's the idea. Okay, so let's look at exactly now the reconstruction system or reconstruction filter. What does it have to be? Now you see from XS sub S, this was our sampled signal. We have the sequence, right? The discrete time signal. But now going back to the continuous time, we need a reconstruction system, right? It is actually, like I said, discrete to continuous filter or system. What do we need? Exactly. I mean, this was the spectrum of X sub S j omega is the spectrum of X sub S t, the sampled signal in time, and this is the sample signal in frequency domain. Now, we will remember this. If this is a filter, we need a convolution in time domain, and that is a multiplication in frequency domain, right? So we need frequency response of this filter. We will multiply it by our sample signal spectrum, right? So this is HR of j omega that has to be designed to obtain our signal back. You see, this is the idea. Now, the reconstruction filter, if we sample the signal correctly, meaning the sampling frequency was at least twice the bandwidth, WB, the frequency, I mean maximum frequency in the signal, the copies of X of j omega did not overlap, as in here. So if we now pass this signal through a reconstruction system, meaning discrete to continuous converter, it's a low pass filter actually. We are trying to really extract this part of the spectrum. We are successful. Let's pick, for instance, the cutoff frequency to be half of the sampling frequency, which happens to be in the center of the two copies of the spectrum, which is good. And we set its amplitude to TS because here the amplitude of the spectrum was divided by TS, right? We reduced by that amount. We now amplify it back. You see, what is this XR of j omega? When I go back to the original time signal, can I go back to the original time signal? This is exactly that, right? So this XR of j omega, remember, look at the spectrum in the bottom. It's exactly the, here, the original spectrum, X of j omega. The signal we sampled was this guy, the continuous time signal. And now we captured it back. So we converted from continuous to discrete now to this discrete to continuous. That's the idea. But, okay, what is this ideal reconstruction filter before we go to actually aliasing or distorted version? Remember, here you should just maybe recall a rectangular signal like this in rectangular pulse in frequency domain is a sink in time domain, and it's vice versa, right? A rectangular pulse in time is a sink in frequency. So this is Remember, this is the mathematical definition of the filter in the frequency domain, a low-pass filter with amplitude Ts. Whenever the frequencies are less than pi over Ts, right? We have Ts. So let's say, why did we have it? Because we have omega s over 2. So that is 2 pi over Ts, but over 2, that's why I have the cutoff frequency at pi over Ts. And this is in time domain. Okay, I should probably get rid of that box. I mean, this is the HR of T, exactly. So I was trying to show this actually. Okay, it's already there. Okay, okay, we can't see it somehow in here, so, but it's this guy, so it's fine. This is the inverse Fourier transform. This guy is of the rectangular pulse in frequency domain. It's, you see, a sinc function. Here the argument of, it's a sine t over t, but the argument, the parameter is actually the cutoff frequency, pi over Ts. Remember, we said this was omega cutoff, let's say omega c before sine omega ct over omega ct. So you see, guys, this is a sine, but which is divided by t, right? That's why it's decaying actually. As t goes to infinity, it's going to 0. That is what is called the sinc, right? Sine t over t type signal. So it's really not the same sign repeating itself, not periodic, but it's really a decaying sign. And it's an infinite extent signal, right? Is this filter realizable? It's an infinite time signal. It's an ideal, actually, signal or ideal filter. It's what we call an ideal low-pass filter, remember? And for the sampling problem, it's an ideal reconstruction filter also. Why ideal? Because with this filter in place, we can perfectly reconstruct the signal back. Are there any questions until here? Do you guys see what I'm talking about at this point? Okay, here is the point here. Okay, look at the main lobe of this sinc, meaning the maximum value at the center. It's centered and symmetric, right? Nicely. So we will now see in time domain what is happening in this ideal reconstruction, which was very easy to see in the frequency domain, actually. In the frequency domain, ideal reconstruction was really multiply this sample spectra at the top by a low-pass filter spectrum, frequency spectrum. Just multiply them. We get rid of all the copies, extra copies. These were all cleaned. We are left with the center one, center spectrum, which is the original spectrum. It was very easy. Now, in the time domain, let's analyze this. We will see, guys, in the time domain, actually, okay, these are, you see, it has a maximum value at the center lobe, and it actually has zeros at the multiples of the sampling period, Ts2, Ts. So now discrete to converter, discrete to continuous converter in time domain, it does an interpolation actually. Remember your numerical methods course? Remember we had polynomial interpolation. We had some basis function, right? For instance, polynomials that was actually shifted and multiplied by the values of that signal that we were trying to interpolate. Here, exactly this filter or this signal is a interpolator basis function. Okay, you will see that here. What we do in time domain is convolve this interpolation filter HR of T, which is the sinc with the sampled signal. And remember, the sampled signal has this form. It's the samples at multiples of Ts, separated by Ts or sampling period, times some impulse, shifted impulse. So convolution with impulse is the easiest thing we like to do, or it's the most straightforward convolution. You just shift the signal that is being convolved by the shifted delta. So you see in the end, our reconstructed signal is these signal values between which we are trying to interpolate times the reconstruction filter, or this basis function, like the polynomials shifted to these multiples of the sampling period. So in the end, this is the ideal interpolation formula. Band limited says, it says band limited, it's this ideal low pass filter, and we have an ideal band limited, actually not ideal band limited, a band limited input function, input signal. Okay, so I mean, it's trying to say the sampling frequency was correctly selected, the signal was already band limited, sampling frequency is selected at least twice that band width, and we use the ideal reconstruction filter, which is a sinc in time domain, sine t over t, of course shifted. Okay, shifted to multiples of this sampling period, Ts, you see. And the frequency was pi over Ts. Okay, and that brings us to, we just rewrite this in terms of a theorem. This is called Shannon sampling theorem. This sinc interpolation is the ideal perfect reconstruction. I mean, we've just seen it's this interpolating basis function, right? So let's see a signal with band limited Fourier transform such that x of j omega is 0 for outside the range of omega b frequencies can be reconstructed exactly. This is important from samples taken with sampling rate Ws at least twice the Wb, okay? The bandwidth of the signal, that is twice the bandwidth of the signal, and we have our interpolation formula. You see what it does is, guys, please pay attention. Take all those samples we took, so x of 0, x of ts, x of 2ts, x of 3ts, on the other side, x of minus ts, minus 2ts, etc., and multiply them with shifted versions of the basis function, which is a sinc, and sum them up. That's it. This is something I hope you guys also recall from your numerical methods course with the polynomial interpolation. You see, all those things should be tying in your mind, like getting together, because once you graduate, actually, you are supposed to make use of all these different tools, mathematical tools, also implementation tools, to come up with solutions to given problems, right? You will be the engineer or the scientist who is supposed to know and bring all these things together. Yeah, you recalling what you learned, or recalling where the resources are, where the tools, mathematical tools is fine. You don't have to memorize, but you should know somewhere in your mind, make these connections. I mean, these things exist. So reconstruction in time domain, we can again show it graphically in the slide. Remember, we have now a discrete time signal whose samples are x of 0 with the square parentheses, x of -1, x of 1, x of 2. You see, guys, we have, of course, however many are non-zero, we have them. And we have shifted sinc interpolating function. Here, for instance, it's itself at t equals 0, that sinc interpolator not shifted. Here it's shifted to minus ts, sinc interpolator. You see, sinc interpolator is shifted to plus ts here. I hope you see my mouse. And sinc interpolator is shifted to plus 2ts. Of course, this will be done however many times needed. And it is also scaled, multiplied by the value of the, actually here, x of 1 was, for instance, let's say, I'm just making up -1, so it's scaled. X of 0 was 1 over 2, let's say, so again, sinc is multiplied by -1 over 2. X of -1 was 1, let's say, So multiplied by 1. Now we add all these shifted and weighted sinc interpolating functions, add them. You see the nice thing, I think maybe you can tell the amazing thing, beautiful result here is you get exactly the original continuous time signal. There is no loss. Although you discretized it and just saved or recorded every TS value, right? In the end, we are able to go back to or interpolate back to the continuous time signal perfectly, which is great. I think it's a beautiful result. Okay? And we've seen how easy it is to see or prove in the Fourier domain, right? We just used here, it was a sinc filter in time domain, but in frequency domain, that's a frequency, that's a, sorry, a low pass, ideal low pass filter, rectangular form. Just multiply the spectrum to get rid of all this replica, and we get the original signal. So here is a summary. Ideal continuous to discrete and discrete to continuous converter. You see on the left, we have analog to digital or continuous to discrete converter going from continuous time signal x of t to x of n. This is the ideal sampler in frequency domain. At the bottom, you see we show what happens to the sampled signal spectrum. I mean, we just take its samples to get to this discrete time signal, but this is the spectrum. You see, it's just copies of infinitely many copies of the original spectrum. This x of j omega is the spectrum of the input signal. Okay, now on the right, we see the discrete to continuous converter. Remember, discrete time signal comes in. I mean, we say this is really just saying, hey, this was just a sequence of numbers, but now I'll write it mathematically as numbers times shifted impulses, right? To be able to write it as sub x sub st. So it's shifted impulses. Now, this guy goes through a reconstruction filter, remember, which is a low pass filter, and we get the reconstructed signal. Here it is. This is the mathematical equation. X of n is the sampled signal value at the corresponding NTS point or sampling period times n, and the sinc interpolator. But you see, guys, in time domain, this is the representation, but in the frequency domain, it's very easy. It's really just easy to show or express. Multiply the frequency response of the reconstruction filter by the spectrum of the sample signal, this guy, and we get spectrum of XR. Guys, this first line in yellow was the time domain representation. So here of what is happening of these two operations, I mean. So you see on the left, the time domain sampling was very simple to show. Xn is actually the discrete time signal x square parentheses n is equal to x, the continuous time signal sampled at every TS seconds. Okay? It was easy to express in time domain, but it was also still easy to express in frequency domain, as you see these infinitely many copies of the original spectrum shifted to multiples of the sampling frequency. But on the right-hand side, the time domain reconstruction looks a little bit more difficult, though not that difficult if you just know this is a sinc interpolating basis function shifted to multiples of the sampling period. But it's super easy in frequency domain to do the reconstruction, because we know we just multiply the input spectrum, which is x sub s j omega, with the filter's frequency response. Okay? Any questions until here? I think this summarizes the sampling. In the past years, I was writing these in notes, but this year I thought it may be better to show these from the slides, guys. I mean, it's the third pandemic semester, so I know you guys are hanging in there. So I hope these slides were illustrative, easier to understand. This slide really nicely summarizes what we've studied in this first hour. I think probably this slide also tries to summarize what we've studied. It's not the wrap-up course, but still, let's just go over it. It tries to say all signals have frequency content. I wanted to say this next week. I'll repeat it, right? Filters alter the frequency content, okay? And currently, we've learned two domains for analysis, right? Time and frequency. You guys should know for data analysis, these are two important domains. You can analyze data in its original time domain. For instance, for this case, I mean, it's time. For images, for instance, it's a spatial domain. There is also frequency domain where you can transform this signal and analyze its frequency content, right? We've learned these. Actually, there are interesting things like in physics, actually, guys. The signal you record could be coming in frequency domain, the measurements. So this is, for instance, happening in MRI, magnetic resonance imaging. The signal is recorded in Fourier domain. We take inverse Fourier transform to capture the spatial MRI signal in 3D, for instance, or 2D. It's an image. So knowing these are important. Who knows? Maybe you will work in medical image analysis. Who knows? So for your Master of Science, for your PhD, or as a computer engineer. So I think, okay, this is summarizing the Fourier transform by saying it's really mathematically elegant theory. We know forward Fourier transform is shown here. We've learned this since last week. Take an input signal in time domain, projected onto this basis function, e to the minus j omega t. Remember, this complex exponential or complex sinusoid is a basis function, because in this course we learned we can write any signal as sums of sinusoids, okay? And this is shown here. We write any signal x of t as sums or integrals. In this case, it's equivalent, right? Integral of sinusoids at varying frequencies, omega here. Sinusoids are oscillating signals, right? These oscillating sinusoids, or sinusoids oscillating at different frequencies, because we try to capture which frequencies or the weight of each frequency component. And weights are x of j omega, which are our Fourier transform coefficients, okay? So you see, this is really signal decomposition. Decompose your signal onto these basis functions. So I have weights in this transform domain that tell me the weight of each frequency component omega. I hope it's clear. This can be really mentioned as a mathematical elegance. I think one of the biggest probably findings in, was it 1700s? So 18th century, Joseph Fourier, one of the, I think, most celebrated mathematicians of the past 2 centuries. So you should really know and respect and know these theories, because you guys will be, like I said, most of you will, some of you will work as software engineers, maybe computer architecture, cloud computing. Most of you, I believe, will try to work on data science, or somehow will touch or be involved with data analysis. So it is really imperative, or it's a must that you guys know that data has frequency content. It may have oscillating behavior, periodical, repeating behavior, and that might be a feature that you should really capture and analyze. Okay? All right, so I think, I hope for all of you at the end of this course, I'm hoping our IT computer engineering graduates will be able to say, I can analyze data in its time or space or however many dimensions it has in the original domain, space, time, or this multidimensional domain, or the frequency domain. Of course, then if it's a multidimensional signal, this frequency domain will be also multidimensional. For instance, for an image, now our frequencies are spatial frequencies, okay? 2D. I need two frequencies then. Okay, so guys, this must have been the last slides in the past. So it ends with some messages, but I think before that, I wanted us to do a little bit modulation, or if you want, we can give a break actually. Yeah, let's give a break. Any questions? Is the sampling, or at least, guys, we studied sampling as an application of Fourier transform actually, right? It's such a versatile, very useful tool. I wanted to show you that it was very easy to study sampling a signal, right? This continuous to discrete conversion, discrete to continuous, using Fourier transform. It was very smooth. That's what I want you to see. Okay, so let's then give a short break. Guys, and come back almost 9:30. So okay, let's come back around 40. Okay, 9:40. See you then. So let's recap after the break. I think I wanted us to just take a look very quickly before we go to discrete time Fourier transform modulation. This is amplitude modulation. Another application of Fourier transform where you can really very easily analyze what is happening in modulation systems, okay? Amplitude modulation. But we are just responsible from the most basic amplitude modulation, okay? This is from before, the properties of actually Fourier transform. Here is what we wanted to do. Remember, we said, actually you guys now know, signal multiplier is a unit that we know how to analyze, right? In both time and frequency domain. This is called a modulator. And in the sampling, actually we, in a way, modulated the signal by a periodic impulse train, right? In amplitude modulation, we use a cosine or sine carrier wave, sinusoidal. And we know multiplication in time domain is a convolution in frequency domain. Okay? So that's why we carry out a convolution. And here in this case, carrier or the multiplying signal is a cosine. And when we do a convolution, we know actually cosine signal has a frequency spectrum, we know, right? It's two impulses at plus minus the frequency of the cosine signal, right? And here is a pi, which is a normalizing constant. It's fine. Remember, for the Fourier series representation, for Fourier series coefficients, we didn't have that pi. This pi comes from the Fourier transform representation. It's fine. Now you see modulation of a signal or multiplication of a signal x of t. That is the signal to be modulated, guys. In telecommunication, remember I told you about this before, I think in the first few weeks of the class. Let's say I want to submit or send my voice or your voice through a telecommunication channel, right? And however, we know that the receiving end, the receiver needs to obtain a high frequency signal because of the antenna sizes, and also we need to actually decrease the wavelength, increase the frequency of the signals to be transmitted. Of course, these are telecommunication theory. We are not fully responsible, but we should know the mathematics which says I can take the spectrum of a signal x of t, which is x of j omega, to high frequencies by convolving that spectrum by, with delta, right? Actually two impulses. Here it's at plus minus 1 because of the cosine, actually, because it's symmetric. So I can actually really convolve the spectrum with this of the original signal with the spectrum of the cosine. That's what I'm trying to say. And spectrum of the cosine is two impulses at plus minus omega c. And that will really, that convolution shifts my spectrum to plus minus omega c. Remember, actually sampling in the first hour, we did very similar thing. There, these replicas were infinitely many. Remember, the input spectrum was replicated infinitely many times. Two multiples of the sampling frequency there. Now this is shifted only to plus minus the modulating carrier frequency, omega c. That's the only difference, guys. Here, you see, this is the modulating carrier signal. So x of t, okay, here it says x of t modulates the amplitude of the cosine. This is a telecommunication convention, it's fine. So this is the carrier signal. X of t modulates the amplitude of the cosine wave. That's correct, actually. So you see, now we have in the frequency domain two shifted copies of x of j omega. This is it. All right. And at the end, actually, of the modulator. So this is another system. I'm just giving you another system. We're studying amplitude modulator system, okay? And at the end of the, or output of the amplitude modulator, we have the y, which is x of t times the carrier signal. We've seen this before. This is the output of the modulator, the spectrum of the amplitude modulator. So let's say if I had this signal at the input, this is trying to say, this is a pulse minus rectangular pulse between minus plus t, right? When you see this simple mathematical definition, just in your mind, visualize that signal. I know its Fourier transform is a sinc, then I would have sinc translated to plus minus WC. This is just a actually exercise slide. Now, I would, let's see here, two things. You see at the, actually, look at the bottom. This is the y of j omega, right here, the y of j omega, two sinks actually. You see at plus minus omega c, these are those sinks actually, shifted to those two. Okay, so I'm trying to see now, we want to now at the receiver, we want to, I'm going to come to that actually, we want to see the deep modulator signal, okay? But before that, let's see. Okay, we've already said this, two exact copies. This is showing the signal, the modulated signal in the time domain, guys. Y of t is x of t times cosine, the carrier signal, the cosine omega ct. So if, let's say, this was the input signal to be modulated and transmitted, okay? Amplitude modulation, this is a telecommunications application of Fourier transform. And then the modulated signal you see is this envelope. This is an AM signal, by the way, AM radio waves. Now we use FM mainly, but still, this is the birth, the original, actually, entry of modulation systems into telecommunications around 1930s, 40s. Maybe a little bit before, right? Beginning of the 20th century, amplitude modulation. Now you see, this would be the amplitude modulated signal, and in the spectrum representation, actually, my input signal, let's say it had a band limited form like this, it would be shifted to plus omega c and minus omega c, okay? And half amplitude. This was A, now this is A over 2. Now, my question is, I'm trying to come to the demodulation, the receiver. So this signal at the bottom is transmitted. Okay, that is a high frequency signal. It has traveled through the communication channel. Now at the receiver, there is a receiving antenna, some device that measures or captures this, how to demodulate, meaning how to go back and reconstruct the transmitted original signal. Okay? Yes, this is already frequency shifted copies. And yeah, we sometimes talk about, I told you this in the first hour, let's say this white half of the triangle to be the upper sideband, low frequencies, the yellow shaded part to be the lower sideband, the negative frequencies, okay? Now, that is my question. We are studying two systems actually. It is very, I think, a good example because, and these are very good examples because we really see with the help of the Fourier transform mathematical tool, we can easily analyze these systems. Modulator, we've already seen its effects. It's really taking the signal spectrum at the top, pushing the spectrum to plus minus WC. Now, what is the demodulator? So demodulator is the system at the receiver. Modulator is the system at the transmitter. Okay? I need to bring back the spectrum from plus minus omega c back to 0. So I need another multiplier by cosine actually. So you see, this would be the form of the demodulator. I want to multiply the coming signal by this time another carrier signal with the same frequency, of course, actually the same carrier signal, this cosine signal, and pass it through a low pass filter to get rid of unwanted spectra at higher frequencies. This is, now you will see this system, the modulator system, it's very easy to do in or follow and analyze in Fourier domain. So let's do this. You see two components, multiply by cosine and pass the signal through a low pass filter. Multiply by cosine, this is analysis in time domain. Okay, you can just do this manipulation, but in frequency domain, actually you see, this is much easier. I capture the original signal spectrum and two more copies, this time pushed to plus minus 2 omega c. Why? Let's check this, and then I do a frequency multiplication, right, by frequency domain multiplication by the filter. Actually, now see how easy it is to follow in Fourier domain. This is the signal obtained at the transmitter. So this is input to the modulators, demodulators. Multiplying this signal in time domain by cosine pushes this or shifts this signal to the 2WC, right? Sorry, the center is 0. So pushes it to WC and minus WC. Actually, that would be exactly, then add those two, that would exactly give us the spectrum at the bottom, guys. So you see, I have accumulated, nice, I mean the two replicas of the original spectrum in the middle, which is great, that's what I want. And I now have two extra unwanted spectrum at 2WC and minus 2WC. That would mean once you look at the spectrum, you would say, I need a low pass filter to extract my original signal spectrum, because at the output of the demodulator system, I want to really get as output my original x of t, the transmitted signal. So my filter should have a cutoff frequency, which should obey some criteria, and it should have an amplitude, which is 2 because the amplitude was held. Now, can you tell me this, what constraints this cutoff frequency should really satisfy? Look at, it's very easy to see here. It should be greater than omega b and less than 2 omega c minus omega b. Remember, this is 2 omega c, my mouse, the center of the spectrum, and minus omega b, this is the bandwidth, right, half bandwidth. And then I have actually this left-hand side of the spectrum, of this high frequency shifted spectrum, giving me the upper constraint. So exactly this criterion. Cutoff frequency should be less than 2 omega c minus omega b, greater than omega b. So you design a low pass filter in your demodulator system in this way. That's it. And in the end, this is the low pass filter. You see the dots here. And you have actually multiplication of that with the spectrum will eliminate these unwanted high frequency spectrum, and we end up with actually the original spectrum in the middle. That's the original signal. This is it actually. This is the idea behind amplitude modulation, guys. That's it. I don't know, is it clear? Yeah, the general idea is clear, right? Okay. So then people, of course, said, now we can use multiple. This is frequency division multiplexing. I'll just go over this very quickly. For instance, AM radio band is, let's say, 530 to 1620 kilohertz. Then I need to have multiple channels. So I need to place, let me show you, multiple frequency bands of amplitude modulation, meaning, for instance, some of the signals that will be in channel, radio channel amplitude, AM radio channel 1 will be modulated by cosine omega C1t. The second channel, the signal will go through the second channel. It will be played there. So it should be modulated by omega C2t. Do you see what I'm saying? Now, then they will be placed in this frequency spectrum, hopefully not overlapping. You have to be careful. And the spectrums of inputs should be band limited. That's why typically we do a low pass filter a little bit. And we need to be careful about overlaps between the frequency bands. This is the idea. But then you would have to, at the transmitter, at the receiver, extract the corresponding frequency band. This is the idea behind AM radio channels, actually, multiple radio channels. Okay, so maybe, I think this may be a little bit more details, but this is exactly what is happening. Different listeners or channels are tuned to different bands, the frequency bands. So here you see we were using a bandpass filter at the receiver to extract the corresponding channel signal, or the signal that is really targeted or sent for your channel. You are tuning to that station actually. This is tuning by bandpass filter. Okay. I think this should be fine. This was a quiz from the last years. I think your assistants will be coming with a quiz. Let me see. Okay. I'm not going to the, why am I not going to, let's see. Because I'm not sharing, am I sharing at this point? Yes, I am still sharing. It's going to different desktops, guys. So I want to know, okay, guys, that was the end of the amplitude modulation, the sampling. Now I want us to go to discrete time Fourier transform if there are no questions from there. So we have this topic left, discrete time Fourier transform. I'll try to go wherever we can go to this today, I mean, until time allows. And next week we wrap it up. Okay, that should be it. So this is like the last topic, and with DFT also. So this is, guys, chapter 7 from DSP book, digital DSP first book. So let's see. So now from continuous time Fourier transform, we go to discrete time Fourier transform. We already generalized the frequency response concept because we've already studied continuous time Fourier transform. This book doesn't study continuous time Fourier transform. We're studying from two books. But we already established general concept of frequency domain. Okay. So, I mean, this is just to recap the frequency response. Remember, we had an impulse response and its corresponding Fourier transform, but let's go to actually definition of discrete time Fourier transform. Guys, recall your continuous time Fourier transform definition. That was an integral. We had e to the minus j omega t. Now we are working with, when we say discrete time Fourier transform, now we are working with a discrete signal. Before we were working with a continuous time signal and we were studying its Fourier transform. Now we study Fourier transform of a discrete time signal like x square parentheses n, okay? So that brings us to a sum, right? In the forward transform. Why? Because my n is an integer variable, okay? Discrete variable. But now I'm using normalized frequency, radian frequency, omega hat. Remember, omega hat was, what was it? Omega times Ts, right? Or normalized omega over Fs actually, omega hat. It's continuous still, and is discrete here. So this is my basis functions in this case, e to the minus j omega hat, and we've studied this in frequency response actually. So this is called my discrete time Fourier transform. You see, again, I'm projecting my signal on this basis function to find these coefficients. These are Fourier transform coefficients. Now, the inverse discrete time Fourier transform is, you see, again, decomposing the signal or writing the signal as sum of or integral of, because my omega hat is continuous here, integral of actually this, the coefficient, Fourier transform coefficients multiplied by the basis functions. Or this is really, again, projection of the Fourier transform onto, again, the basis functions, inner product of x of e to the j omega hat with to the j omega hat n, okay? This is, this time, what is different from since past week, I think last week, we've been studying continuous time Fourier transform. Omega could take any value, minus infinity to infinity, the frequency. Now, again, we are back to, remember from our frequency response weeks, a periodic normalized radian frequency. It has a period of 2 pi. Okay, so I mean, this means when I add 2 pi to my omega hat, okay, I know I'm actually incrementing omega hat by 2 pi, but its effect on the spectrum is the same. So I'm really coming back to the same place. So you see, just maybe here, you can show this is true. This discrete time Fourier transform is always periodic with 2 pi. Add to omega hat 2 pi, because e to the j omega, e to the j 2 pi n brings me, it's 1, right? It's on the, remember, on the unit circle in the complex plane. That's 1. So I would end up with the same spectrum. That's what it's trying to show or say. We've all, I think, shown this before. Okay. So we define discrete time Fourier transform for the first time, but actually we've studied with frequency response, discrete time frequency response, which was really this guy before. I mean, it's the same thing as we studied before. But inverse, I think we are seeing it for the first time. Okay, some extra information. What is a transform? We change problem from one domain to another domain to make it easier. Here in this course, it's time and frequency domain. And of course, it has to be invertible. When I go from time domain to frequency domain, I need to come back, right? Because I can transform to frequency domain, do my manipulation there, signal manipulation, and come back to the time domain again. Inverse must be unique, exactly. Periodicity is shown here. I was talking about it a few slides ago. Add to your omega hat multiples of 2 pi. You're gonna end up with the same spectrum. So discrete time Fourier transform is periodic with period 2 pi. Okay. Guys, these are really things we've studied already in continuous time. That's why I'm showing on slides and going through slides, which may look a little bit faster. But existence of discrete time Fourier transform, when does a Fourier transform of a signal exist? Remember, we've shown this last time, when that signal is absolutely integrable for a continuous time signal. When, for a sequence or for a discrete time signal, when it is absolutely summable, my discrete time Fourier transform exists. Okay? So it applies to discrete time sequences regardless of length, because you see the sum is infinite here. Here we just apply definition of the discrete time Fourier transform. X of e to the j omega hat, remember, it was equal to sum, an infinite sum, the signal times the basis, Fourier basis function. I mean, with the conjugate symmetry, of course. I mean, the conjugate with the negative sign here. Take the absolute value here to know when the sum converges, because when it diverges, I can't calculate a discrete time Fourier transform. You can see that when the signal is absolutely summable, meaning this sum is less than infinity, it's finite, I can calculate a discrete time Fourier transform. Okay? This tells me when the signal satisfies this constraint here I'm showing, I can find a discrete time Fourier transform. It exists. But there are some signals, like for instance cosine omega hat n. It's not absolutely summable, but its Fourier transform exists. It's a periodic signal. We know for some signals like that, we know the Fourier transform also exists. For instance, if the signal is a single sample, it's a delta n, right? The impulse, unit impulse. What is its discrete time Fourier transform? Very simple, apply the definition. The signal is delta n, remember, impulse. Apply the definition of the Fourier transform. We end up with 1 actually. Remember, this is again very similar dual relation. Very narrow signal in time, it's a constant signal in frequency. So we know this. This is a Fourier transform pair. Very similar to what we've studied last week in continuous time. Impulse function, its Fourier transform is a constant function in frequency domain. Okay? Now shift that impulse, unit impulse, down to nd. I mean n equals nd, delay. Remember, Fourier transform magnitude is the same, but it's gonna have now, it's gonna have this multiplication by this complex exponential, which is e to the minus j omega hat times nd. The time shift comes as a phase shift actually. You see, magnitude is the same, but I introduced a phase shift. By the way, this Fourier transform is complex function. So we have a magnitude and a phase. I think we're going to show this soon. Generalizes to the delay property. Remember, shift a signal or delay a signal, its Fourier transform will be actually multiplied by a complex exponential, meaning a phase shift will be introduced. This, remember, this e to the minus j omega at nd is a phase shift because it goes to the, it affects only the phase of the Fourier transform, not the magnitude. Any questions, please, always you can stop me. So we can find the discrete Fourier transform of a right side exponential signal. First, remember, we've learned such functions or signals. For instance, step function, remember, it's all zeros in the negative time axis and it's all ones in the positive time axis. This is the discrete version of u of t or Heaviside function, u of n. Now, we have a right-sided exponential in discrete time, a to the n, a is less than 1 to have this decaying exponential signal. and we want it to start at n equals 0, let's say, we want to give it a starting point. We multiply this a to the n by u of n to get this right-sided exponential signal. Now the question is, what is its Fourier transform? You see, we are developing again, as we did in the continuous time version, these pairs of time domain signal and its Fourier transform. It's really, guys, please sit down, take a piece of pen and paper. It's very easy. You can calculate just by applying discrete time Fourier transform formula. You see my sum now starts from 0, goes to infinity. I inserted the signal a of n, u of n actually, right? In this case, here. This is the basis again. Do the math here. We use the geometric sum formula, guys. Remember, because this has magnitude less than 1, I have a geometric series formula. This was, let's say, alpha to the n. Then this sum corresponds to 1 over 1 minus alpha. Exactly, my alpha is a e to the minus j omega hat here. Okay. Any questions? Actually, please ask. All I'm doing is applying the definition of Fourier transform to find or calculate discrete time Fourier transform of some specific signals that we know, because then for other signals that can be written as combinations of these known signals, we can use the table of Fourier transforms. Okay? This slide is also nice because it says we can now view the discrete time Fourier transform also as a complex function and plot its magnitude and angle components, or plot or analyze or just calculate. So let's start with this Fourier transform. You see it's a complex function of normalized frequency omega hat. I can convert this into polar form, right? A magnitude times e to the j a phase. So we can, to find its magnitude, we can take the Fourier transform and its conjugate, multiply them, because then I can always take its square root, right? And here, apply the Euler formula here, guys. Open this up by cosine, sine, cosine, sine. Do the multiplication. In the end, you'll end up with this magnitude response, or it's magnitude Fourier transform, actually. We've seen this in the frequency response, and the same thing now by the derived version. This is, you can find this in chapter 7 of DSP first textbook. Also, the phase can be found by, of course, by dividing this would be the numerator phase over the denominator phase, right? Minus a sine omega hat. We didn't derive it fully here, so currently I can't really say on the top of my head, but this should be, again, easy to read off from the form of the derived expanded Euler form. Using Euler expansion, you derive this. You know how to find the phase of that complex function, okay? This is, again, relies to your calculus skills from the freshman year. Now we can plot these, magnitude and phase. We know magnitude is an even function, phase is an odd function, because the input is a real signal. We know this property of, again, Fourier transform. So let's look at this plot. You see even function. So what this plot tells me, this is the Fourier transform coefficients. For each of these frequencies, you see between minus pi and pi. Now, remember this difference. Until this hour, for the past continuous time Fourier transform lectures, omega, the frequency was minus infinity to infinity. Now it's minus pi to pi again, because we're talking about Fourier transform of a sampled signal. So this amplitude tells me the weight of each frequency component in the signal, right? That's why it's important. So for the zero frequency, it has a large amplitude. So this is a more like a low pass signal, right? It has more dominant low frequencies, and frequencies fall to zero at the high frequencies, minus pi to pi. Then the phase response or phase Fourier transform tells me the amount of phase shift at each corresponding frequency, and you can see it's an odd function of frequency or omega. Are these plots clear? I mean, this is a plot of course, this function. You would have to resort to some numerical computation or NumPy, or, you know, I don't know what is your platform, Python. I think in this course we're using Python, of course. You probably you've done these in your assignments, right? And this is also just numerically computing this arctan minus 8 sine omega at over 1 minus a cosine. So now my question is, we've seen this pair of Fourier transform, right-sided exponential in time domain, Fourier transform 1 over 1 minus a e to the minus j omega. If we didn't know that, and if we said, hey, I'm given this Fourier transform, this is a signal that is represented in Fourier domain. If you ask me what is the time domain signal, you may want to resort to the equation, definition of the inverse Fourier transform, insert this form of the Fourier transform here, find this integral. Can you? It's putting two question marks here. It's not something that you can really evaluate or calculate. You see, that's why it's good to know these forward and backward Fourier transform pairs, so that when you are given this, okay, I know the form of this in time domain already from my Fourier table. Okay, so this would be 0.3 to the n u of n. This is the Fourier transform that corresponds to that signal, which is 0.3, right, to the power n u of n. Okay, this is clear, I hope, but I'm trying to make, like, the point I'm trying to make is clear. Okay. So now let's look at further examples here. This is a sinc function. Guys, these are the reason I'm showing on slides is very similar to what we've seen in the continuous time. Now, for instance, we start with a sinc in time domain, sine n over n, right? Type of function. So it's a sine which is decaying actually, because it's divided by the time variable. And it's a discrete time sequence, of course. It's only these, we have these samples of these red dots. So now my question is, what is its Fourier transform? If you didn't know your Fourier transform theory and these tables, right, the pairs, good luck again in calculating this infinite sum. It's probably not possible to evaluate, not calculatable, okay? This is really naively applying the Fourier transform formula. Instead, you guys would be like, hey, I know already an ideal band limited signal. This is a, you see, low pass filter. I wish I can write here, but unfortunately I can't. Guys, this is really a rectangular low pass filter, right? Its cutoff is 0.2 pi. This guy. It's a spectrum in a low pass form at cutoff 0.2 pi. It's 1 for omega hat less than equal to plus minus 0.2 pi. It's 0 else. Now I know I can start here, apply the inverse Fourier transform formula. You see, it's 1 in between minus 0.2 pi to 2 pi. I can do this math, it's easy, and I arrive at a sinc, which is sine 0.2 pi n over pi n. And then I know, now given a sinc function or sinc sequence, I know its Fourier transform is a low pass filter. Okay? This is what I'm trying to say. We just verified it here. You see, we started from the discrete time Fourier transform, used inverse Fourier transform formula to go back. Yes, here it says it's good to know this discrete time Fourier transform pair. So we know this pair, a sink in time domain, sine omega hat b n over pi n. It's a low pass filter in Fourier domain with the cutoff frequency given by the sine frequency, sink's frequency, okay? Exactly. This is summarizing that slide. This is a sink function, sine omega hat b n over pi n. Its Fourier transform is a low pass filter with the corresponding cutoff frequency. Just remember this picture in your mind, okay? Now we will do the other way around. Start with a rectangular pulse in time domain. Find its Fourier transform in frequency domain, okay? So this is a rectangular sequence or pulse of length L. Its definition is given here. Now apply the discrete time Fourier transform formula. So I will just have to sum from 0 to L minus 1. It's the definition of the signal, right? I have the signal only non-zero here. It's 1 times e to the minus j omega hat and use again this finite sum formula from our calculus. This is already known. Guys, don't be surprised. This was something that we can look up. Okay? And open this up. Can you, from here, can you go to here? How would you go? Look at my mouse. From here to here. Just take this into a Fourier, into a sum. Maybe we could have written some of these. Normally I was planning to write these, but I saw everybody is a little bit tired, so maybe we could, I thought maybe we can maybe share. What was the signal? Guys, let me see. It was, this is just a side. So I had a rectangular pulse like this, right? 0 to, I think, length L. This was L minus 1 and this was my x of n, right? Now we're looking at x of e to the j omega hat. This is 1. 0 to L minus 1. Okay, let's go to blue color. E to the minus j omega hat n. And we know from, this is known, I mean, already. This is j, let's say L omega hat. Okay. I mean, you can think of this as alpha. I think we have this formula, right? Alpha to the L over 1 minus alpha. Recall this. I mean, this was from your calculus. This is equal to this guy, right? I think you can recall. We use this one. This is equal to that. So now I want to go to that sine over sine form, which is called the Dirichlet function. I will do, remember, we've been doing this trick from the beginning of the class. I take this into a parenthesis of L over 2, the half frequency, e to the j omega hat L over 2 minus e to the, for the numerator, for the denominator, I can do a very similar trick with the omega hat over 2 minus e to the minus j omega hat over 2, right? Do you guys see from here how to go to here? I mean, it's really just taking the function into parentheses of, in the numerator, e to the minus j omega hat L over 2, and in the denominator, e to the minus j omega hat over 2. Now, from here, I can come up with e to the minus j. So I'll take this up, L minus 1 over 2 omega hat, right? This is the thing together. And the numerator is a sine omega hat L over 2. The denominator is a sine omega hat over 2. This is it, okay? And typically, I think we name this a Dirichlet function, this guy. In signals and systems, this guy is called this is defined as a dl e to the j omega hat. I mean, you see L is the parameter here. So it's really a shifted, frequency shifted. I mean, this is multiplying by e to the minus j omega, it will be time shifted, right? I don't need that. Times dl of e to the j omega hat. Okay, this is a sine over sine this time. This is called a Dirichlet function. So I'll go back to the slides. This is, you see, the important thing is this was x of n. Now this is its Fourier transform, x of e to the j omega hat, okay? This is the Fourier transform pair, at least. That's what I'm trying to say, okay? Discrete time Fourier transform pair. So, I mean, the reason I did this is, yeah, because we were in this slide and our slide is showing all of a sudden, you see from here to here. Now you see how we went there, right? I mean, I think you could have done it too, but anyways. So, so summary of some discrete time Fourier transform pairs we've seen, okay? After this, we can give a 10-minute break, I think, because we've studied many material again. You see a delayed impulse sequence we see in time domain is a complex exponential with the corresponding phase shift in the Fourier domain. A right-sided exponential is, you see, such a actually rational function in frequency domain. A sink is a band limited or low pass filter like spectrum in Fourier domain, right? This is a low pass filter and it sinks in time. And we've seen in this case, actually in discrete time, this time the rectangular pulse has this sine over sine, not sink. In the continuous time, it was a sink, but now it's this Dirichlet function, sine over sine. Its form looks very similar to actually sink, but and times a here a phase shift in frequency domain, which will be which would normally look like a delay in the time domain. So let me see if we have any. I was wondering if there are more examples. Frequency domain, yes. I'm hoping you guys have now a frequency domain representation thinking about signals and solving these data problems in frequency domain. You must know pairs of Fourier transforms of certain important signals, know properties and certain key theorems, and be able to combine time domain and frequency domain methods. Actually, it's not really difficult, this course. It's just about knowing these things, okay? Summary of this lecture this hour is we've defined discrete time Fourier transform, right? It's a Fourier transform for a discrete time signal like this, x of n, and inverse discrete time Fourier transform now gives me, given the Fourier transform x, e to the j omega hat, I have to go back to the time signal. So this is from time signal to the Fourier domain representation, right, forward, and inverse transform from the Fourier domain representation, how to go back to the time domain. So I think, okay, so in the next hour, we can cover the remaining things, not this one. Okay, I think we will be covering a little bit more properties of filtering and stuff. I think that should be it for discrete time Fourier transform. Yeah, I mean, that should be enough amount of material. So, any questions from not this one, but here from the discrete time Fourier transform? We are fine. Okay, so let's give another 10-minute break and be back. So let's say be back around at 45. We can do half an hour more lecture and then go to the quiz, okay? So let's meet at 10:45. Thank you, guys. All right, so let's now look at discrete time Fourier transform and filtering. And let's see actually, guys, what we have in our set of slides, last set of slides in discrete time Fourier transform. These are from, guys, chapter 7, section 7 to 7.3. So properties of discrete time Fourier transform, these are very similar to continuous time Fourier transform. We will take a look. And this is one of the main things you should remember from this course. Guys, look at this statement. Convolution is mapped to multiplication. Convolution in time domain is multiplication in frequency domain. This is very important. And we'll look at ideal filters, low pass, high pass, band pass. Okay? So recall discrete time Fourier transform is the math behind the general concept of frequency domain representations now. And the spectrum in this case is still a continuous function of normalized frequency, okay? Before also it was continuous function of frequency, not normalized. And remember for Fourier series representation, it was just discrete frequencies, right? Multiples of the fundamental frequency. And also for DFT, it's gonna become a line spectrum or discrete spectrum. We've seen this in the past hour. I won't repeat this. So we've already looked at these discrete time Fourier transform pairs. This is also something we've seen, conjugate symmetry property for a real value signal. We've derived this for frequency response. And we know now, you guys know now, frequency response is really the discrete time Fourier transform or continuous time Fourier transform of the impulse response function. So this is really the Fourier spectrum, and we know it satisfies a conjugate symmetry. And this is the definition, mathematical definition of conjugate symmetry. Take the negative frequency, take the conjugate of the values of this function, and you get the same function. This is called conjugate symmetric function. We've already seen this. I'm passing because just the previous hour. And properties of discrete time Fourier transform exactly carries over from continuous time Fourier transform. We know Fourier transform is a linear transform. You know what linearity means. It has a time delay property shift. I mean, linearity is superposition, right? Add a few signals together, scale and add them, like here, x1, x2, ax1 plus bx2. You can do the same in the Fourier domain, okay? Time delay a signal, its Fourier spectrum will be affected with a phase shift. Remember, this exponential affects the phase component of the spectrum. Frequency shifts here in the Fourier side. If you shift the frequencies by omega hat c, on the time domain side, you multiply by a complex exponential, complex sinusoid. Here are the derivations for these, okay? Linearity is simple or straightforward to prove. Insert this superposed input signal into the definition, you'll find the superposed Fourier spectrum. This is really straightforward, so Just remember, this transform is linear. This one we can do maybe just it is an educational side. I mean, like the previous one, but now insert a shifted signal into the Fourier transform definition. Do a change of variables, right? N minus ND, name it as M, okay? Name it as M. You will end up with, you can see that, again, the Fourier transform times this phase shift or complex exponential multiplying the Fourier transform. Okay? All right. Properties. Okay, for instance, if I give you this signal now, use properties of discrete time Fourier transform to find the Fourier transform of this signal. You see, it's a rectangular pulse of magnitude 1 in between 0 and n0 minus 1, and rectangular pulse of magnitude -1 between n0 and 2n0 minus 1. Which properties would you need to use, guys? Can you answer? To find Fourier transform of this. It's addition of two signals, right? So we need superposition, we need shift and scale. So once I know Fourier transform of this part of the signal, right? I can calculate easily Fourier transform of the whole signal. Right, guys? Yes. So that's what we do. Let's do that. Exactly. You see, we write y of n as x of n minus x of n minus n0. X of n is this part. And we shift it and multiply it by -1. Shift by n0 and multiply by -1 and add them up. So we use linearity property. And we want to exploit known transform pairs. You see, we don't want to calculate from scratch. This is the known transform pair. This is exactly x of n is this signal, guys. Look, 1 for 0 to n0 minus 1. Here, this pulse, this sequence, rectangular sequence or pulse, and 0 otherwise. We know in the first or previous hour, we showed its discrete time Fourier transform is this sine over sine, the Dirichlet function, times a phase shift. Okay? This is what we derived. Of course, there it was, remember the parameter was L. Now it's just N0. It's the, I mean, L, capital L is replaced by N0. Okay? I mean, you would normally be looking this up from a Fourier transform table. Okay? But you should know, of course, to correctly insert the parameters, right, of the given signal. That's it. So now, okay, we know this pair, Fourier transform, time domain, Fourier domain on the left, right, left is time domain. Now we want to calculate the other side exactly as here. The shifted part will have, you see here, have Fourier transform, the same x, the Fourier spectrum, x e to the j omega hat multiplied by minus e to the minus j omega hat and 0, this phase shift. That is, then add them up. You see, guys, we have the final spectrum. So this y e to the j omega hat is the Fourier transform of this given signal here. It's a sine over sine that also has actually form like this, a main lobe and some small lobes. Here, however, it's addition of the two, so x minus phase shift times x. So in the end, we end up with, when you plot this, I mean, of course, you should plot the magnitude and phase separately. The magnitude looks like this. I mean, you can use, of course, numerical tools like Python or, you know, I mean, it's not possible to directly look at this and plot this on the right-hand side. It's numerically much easier to plot. Okay? Yes, we exploit known transform pair. Another property, frequency shift. Here, look at the frequency side. Right-hand side is the Fourier domain side. Fourier spectrum is shifted by omega hat c frequency, right? on the left-hand side, the signal is really actually multiplied by this complex exponential or complex sinusoid. You can show this by the definition of the Fourier transform. Okay? Look at this definition. I just inserted y of n here, right? And then solve that my actually Fourier basis is shifted here, and this is really the Fourier transform of x with a shifted frequency. That's now again the sinc and this rectangular sequence pair. Okay, rectangle not sequence, sinc in time domain, and the rectangle or low pass filter in the frequency domain. We know this pair, right? I think we derived this already in the first hour, but you can. It's very straightforward. We did this, I think. We started from the Fourier domain, used inverse Fourier transform to go back to the sine n over n type function. Sinc to rectangular pulse. Okay? Here, important thing is the sinc has this sign which has omega hat b frequency here. That goes to the cutoff frequency of the rectangular filter, okay? Omega hat b. This is a pair you can derive now. So, how to do this, okay? Okay, sinc times the cosine or sinusoid. Now, instead of just a complex exponential, I can multiply by a real sinusoid. I mean, a complex sinusoid was here, right? I can multiply this signal by a complex sinusoid or a real sinusoid. This will give me, I know, because this creates frequency shift, right? From frequency shifting property. Frequency shifting. Multiply by a complex sinusoid, it shifts the Fourier spectrum. Now, when I multiply by a cosine, it's a double-sided complex sinusoid, right? It has two sides. Now, it's gonna give me frequency shifting up and down. Okay, that's the idea. Because by Euler's formula, I can open this up, expand this cosine up. You see, it will introduce frequency shift of plus omega hat A and minus omega hat A in the Fourier transform. You see, so actually sine or sinc had this Fourier transform. Now the Fourier transform of this guy will be really the bottom rectangle shifted to minus plus omega A hat, right? And multiplied by 1 over 2 also. That's it. I wish they showed it here, but I think, let's see, is it here? All right, so it's not, but you see what I'm saying here, I hope. Okay, Fourier domain representation of this guy is shifted when I multiply by cosine to plus minus omega hat A. Now this is showing, we've shown this already for continuous time Fourier transform, showing that convolution is equivalent to multiplication. In convolution in time domain is the same thing in multiplication in frequency domain, and equivalent operations. Remember, an LTI system, my signal goes in if I know the impulse response of this system, and I can find impulse response by, remember, sending a impulse function or impulse sequence to the system. I know then I can find my h of n or impulse response. Now, given any x of n, my LTI system calculates the output by convolution of impulse response, which is like the filter function, right? H of n by the convolve it by the signal. This is in time domain. Remember, in frequency domain, a complex sinusoid was being multiplied by frequency response of the complex sinusoid. Now, with discrete time Fourier transform, we know that this convolution operation is equivalent to convolution of h and x is equivalent to multiplication of their Fourier spectrum. We know this. and this can be derived. Maybe derivation is not here, but I think we derive this in continuous time, or maybe it's coming in the slides, but it's not difficult. But this is something, please guys, all of you, this is something that you should remember from this course. At least remember it conceptually. Convolution in time domain, multiplication in frequency domain. So because then that leads us to easy low pass, or not low pass, filtering actually, filtering in the frequency domain. For instance, this is, let's say, my filter, low pass filter. This is the cutoff. And an ideal filter is 1 in the pass band, 0 in the stop band, right? Here, omega hat CO is the cutoff frequency. I know in time domain, this is a sinc function. We know this is a rectangle, Fourier spectra, and sinc is the time domain version. Remember this, right? Now, rectangle, sinc, equivalence, okay. Now, let's say I'm given this ideal low pass filter. I want you to find the output when the input is a sinusoid. Like this. Cosine omega 0 hat n. We know the Fourier transform of this guy because we know this is a periodic signal. We know it's Fourier series, remember? And we know that it's gonna map as two lines in the spectrum, right? At omega 0 hat and minus omega 0 hat. And the question, okay, here you see its spectrum representation is these guys, right? These two lines of spectra, cosine. You recall from the first weeks of this course, we've been doing this because cosines and sines are the main types of signals. We work this in this class. Why? Because they are the basis functions for Fourier transform. I mean, the complex form is the, of course, complex exponential. Real form is cosine and sine. So if you didn't know Fourier transform, if you just know filtering, and if I give you, for instance, this filter, and if you just know filtering in time domain, you would go to its time domain representation, which is a sinc. You would say, hey, I will convolve this sinc with the given cosine. Again, good luck with this convolution. It's not easy to calculate. It's 2 question marks. Instead, tell me the result of this filtering, guys. I'm filtering this signal with this low pass filter. What is the operation in frequency domain? Filtering operation. When I have its Fourier spectrum like this. Please, I'm expecting this from the whole class. Yes, multiplication. Thanks, guys. At least I know some of you are listening. Çağlar, Özgür. So, if we multiply these two, does it pass the input signal as it is or does it eliminate it? It's inside the cutoff. It passes, right? It's in the pass band. So the output is the same signal, guys, here. Spectrum of the input times the TFT of the filter to get exactly the same input as input. But of course, its other frequencies are set to 0 already. Actually, for cosine they are 0. I mean, they are. This is fine. I mean, this is written like this. Don't get confused. It's already this case, right? It's not n. I mean, it's a cosine, the same cosine. It's passed fully. But for instance, now I think there will be other examples. I thought they had another one. Okay, let me ask you, if omega 0 hat was larger than the omega hat cutoff, right? This cosine, if it was filtered by this low pass filter, if omega 0 hat was these, I mean, spectrum lines were outside the low pass filter range, what would be the result of this convolution? Zero. Yes, guys. Thank you. Exactly. Thank you, Evren, Çağlar, Özgür. Exactly. It would be 0. So now remember the ideal high pass filter. This time it is again 1 in the pass band, which would be cutoff to pi and minus cutoff to minus pi, right? and it's 0 in between the minus plus cutoff. You recall this, right? This is a high pass filter. Okay. I can write this as a 1 minus low pass filter in time domain. So then that would be delta n minus sinc. It's time domain representation, and its discrete time Fourier transform is really exactly this one. Let me see. Yes, actually, because we are using 1 minus low pass filter, and inverse discrete time Fourier transform of 1 is a delta. That's why we had this. Okay, so this is a pair then, right? What I'm showing here is a time and frequency domain pair, Fourier transform pair. We can also have band pass filters, right? So again, 1 in the pass bands, 0 in the 2 stop bands. So this filter just passes certain frequency bands between 2 cutoff frequencies, cutoff 1 and cutoff 2. And band reject filter would be 1 minus this guy. So just imagine it, we've studied this before. 1 minus band pass filter. So it's this form. Then its time domain representation is a sinc multiplied by 2 cosine, because remember, sinc is sinc in time domain is a low pass filter. I want to shift it to plus minus 2 different frequencies, and I would have to multiply by a cosine to do that. So frequency shifting up and down is done by cosine multiplication in time domain. You see, now I have form of a band pass filter in the time domain too. Okay. All right. So, another low pass filter example. Again, we have a sinc filter, guys, and it's sinc in time domain, and we love it because it's easiest low pass, ideal low pass filter in frequency domain. It's this rectangle, ideal. And when the signal, input signal, okay, input signal was also a sinc. The ideal low pass filter is a sinc with the cutoff frequency omega hat CO, and the sinc input is a in frequency domain, you see, is again a rectangular pulse with omega hat B bandwidth. Okay, with 1/3 magnitude, you see, that's why it's here. This is 1 magnitude, this filter, ideal low pass filter. The input signal is 1/3 sinc in time domain, rectangle in here. Now, what is the result of this filtering? I'm telling you, I've given you this filter, this is the input. What is the result? Same signal, right? Exactly. Y of n is the same signal, because input bandwidth is less than filter's pass band, which is good. Thanks for replying, guys. Exactly, X itself, you guys said. Now, this is another example. When the bandwidth of the input signal this time was larger than the filter cutoff. Okay, what would happen? Now, it's not the same output, but those parts outside the filter would be suppressed to 0, right? Because it's a multiplication. So wherever it's overlapping here, that would be the resulting signal. So our result would be really now the filter itself. Of course, with 1/3 amplitude, but right, the filter itself. Filter chops off these extra frequencies where omega hat B is larger than omega hat cutoff, because signal bandwidth was outside the pass band. Visually, it's very easy to work, right? In Fourier domain. I hope you guys can see. It's really very, very intuitive. Okay. Okay, I think that's these are some nice examples for filtering. Now I'll also talk about this windowing. This is probably the last thing we want to talk about to get truncated today. I mean, at least we have 5 minutes. windowing to get truncated filters. We want to, guys, this windowing in time domain is devised for the purpose of limiting the input signal to a finite range. So remember the sink, again, look at the sink function, right? Which is the ideal low pass filter in time domain, right? It has an infinite extent, but then it's not realizable, okay? That's why we want to have a truncated sink function, limited in time domain. To do that, we use different window functions. So we will use, for instance, we can use a simple rectangular window in time domain this time. Or here, I think, let's see, using, okay, here it used a in A, used a 25 length rectangular window. So it really just gets this 25 samples, 0 to 25 of this sink, okay? In the second one uses some more smooth window. This was, I think this gray one was the Hemming, yes, 25 Hemming window. So you see it really then in this case suppresses or smooths out, surpasses or suppresses is better, suppresses, reduces the amplitudes of these border values, okay? So you see, in that case, the truncated sink is multiplied by a Hemming window. So those border values are also closer to 0. Do you see what I'm saying? So this slide, guys, shows difference between multiplying the sink by a rectangular filter and by a Hemming window. All of a sudden, why am I talking about these? I'm talking about these because I'm saying now practical filters. I mean, we were talking about an ideal low pass filter, sink, but it's not realizable. It's an infinite extent signal. Now we practically, how can I obtain a low pass filter? This is one idea. I'm truncating the signal to some range, okay? And there are different ways to truncate. We can use different windows. The most probably simple window you can think of is a rectangle, right? Or it could be some smooth rectangular, not rectangle, smooth window function. So let's see the effects of these on the Fourier domain. Effect of windowing in frequency domain. Now you see in A, when we used a rectangular window to do a truncated sink, you see our low pass filter has ripples. It's not ideal. I mean, both of them are not ideal. Remember, I told you before, this is a ideal, not ideal, a practical filter response. The pass band is not completely one. It has some small oscillations. There is a transition band. The transition is not infinite, is not an infinite jump. Okay, with a rectangular window though, I see many more ripples in the pass band and stop band. Stop band also has ripples, okay? So what we did is, guys, we took Fourier transform of discrete time Fourier transform of this truncated and truncated filter on the bottom, in the bottom, to obtain these two frequency domain responses of practical low pass filters. Okay, so you see, by the way, these have become FIR filters, by the way, finite impulse response filters. Why? Because I have just 25 samples, right? It's an FIR filter. So two FIR filters, but they are obtained by two different windows. One is a rectangular window, one is a Hemming window. So in the second picture, the first one is the result of a rectangular windowing. You see more ripples, both in pass band and stop band. The second one, here, this frequency response, it's still a low pass filter. Still there are oscillations. This is not ideal one, but very little. So it's much smoother. But you see also the transition band is really slope, has a certain slope, slowly transitioning. Maybe actually this has a lower slope than this. This looks steeper, but it has more ripples here. But it's nicely, at least smoothly, 1 in the passband and 0 in the, I mean, probably there are some small variations there, but not much. So this would be practical FIR low pass filter, you see? A cutoff frequency, by the way, the WHCO was used was 0.4 pi. Okay? I hope this is clear. So this is how to get a practical filter from the ideal sink filter. So let me see. Frequency. Let me see. Maybe we may want to end here. Okay, yeah, I think we should go to the quiz. We can check later, guys. Please check these Fourier transform pairs. Okay. So we've gone through, I think, almost all of them. This was a right-sided exponential. You can talk about a left-sided exponential too. And properties of Fourier transform, we've talked about. This is discrete time now. Okay? Periodic now in omega hat, linearity, conjugate symmetry, conjugation, time reversal, delay, frequency shift, modulation. We've studied modulation actually in the past, our convolution. Yeah, next time we can define these autocorrelation and Parseval's theorem related to energy of the signal, how to represent it in time and frequency domain. And then that would end the chapter 7, discrete time Fourier transform. And later we have DFT, discrete Fourier transform, where we, like I said, discretize this omega hat too. So any questions until here? I'm trying to see. It's a frequency domain representation of the signal. It's really similar to spectrum representation of periodic signals. That is what it's trying to say. And again, summarizes inverse discrete time Fourier transform. It's a sum in the sense of Riemannian sums in the limit. But don't get confused. It's trying to talk about discretization. We will next time talk about discretization in the omega hat domain. Any questions, guys? I know it's a lot of material. We covered discrete time Fourier transform today. We finished continuous time Fourier transform in the first hour, covered discrete time Fourier transform. And FFT a little bit. So see you next time. I can stop the share and